Okay, that's good. Cool. Okay, go ahead. All right, thanks everyone, and thanks Luca. So I'm going to talk about our second paper, which is called Learning Feed-Forward One-Shot Learners. So this is from the same group of authors, and we're going to be presenting this at NIPS this year. Okay, so first I'd like to introduce the problem of one-shot learning, because it can be a little bit confusing or difficult to define. So we're going to consider it as we want to learn a concept, in this case a classifier, using just a single example per class. So in this case, I have here a bunch of Armenian characters. So from the Armenian alphabet. These are from the Omniglot dataset, which I'll explain later. And we're just going to be given a single handwritten example of the character on the left. And we have to then look at some other characters, examples of characters from the alphabet, and say if they're the same or different. And so our model will never have seen any character in the Armenian alphabet before, but still we want to be able to classify new characters in this way. And so obviously it's not possible to learn from nothing at all. So usually in one-shot learning, you have some examples. So we have like an initial training phase where we have examples from classes that we will not see at test time. So for the example of Omniglot, we have maybe the Greek alphabet here and the Cyrillic alphabet and more alphabets with many or multiple labeled examples for each character. And then we're going to try and learn something from these offline examples such that then we can then do the one-shot task. So I hope that's clear. And the standard approach is to do some sort of similarity learning. So what I mean is we're going to look at the Greek letters on the left, and we're going to say that two characters are the same or the two characters are different. And then hopefully, once we've learned to do that, we can look at some new characters that we've never seen before and say that these are the same or these are different. So that's kind of the standard canonical approach. And so a natural choice to implement this kind of approach is like a deep Siamese network with some kind of logistic regression, so some kind of classification loss. So here we have, you can see the architecture that we're going to consider. So we have a convnet that applies the same operation to two inputs. The dotted lines here indicate that the parameters are shared between the two branches of the network. And then at the end, we're going to take the feature representation of each input and compare them with some function gamma to give us a score, which is f of zx. Okay, so that's the architecture. And to train, to do learning for this, we're going to try and find the parameters of the function f that a logistic loss. So we're going to have our examples will be triples of like an image pair and a label. So for example, if we have two images that are the same, we want to classify it as a positive example. And if we have two images that are different, we're going to classify it as a negative example. Okay. So if you think about it, the approach that we were just talking about in Luca's presentation is a kind of one-shot learning. So we can consider the tracking problem to be a one-shot learning problem, where basically the first example that you get given in the first frame, from that you want to learn some kind of scoring function that you can then apply to new images to find the correct location. Okay, so that's kind of interesting, but it's not clear if it's really practically useful or not, because we could do all the Siamese network approach without really thinking about this one-shot learning. But we started thinking, like, is there a way that we can generalize this architecture so that it's not just a Siamese network and then but maybe something more powerful? And so we actually found the answer by looking at this architecture. So that the final function here, the cross correlation in the Siamese network tracker, what it does is it takes the input or the representation of Z and cross correlates it with the representation of X. So if you think about this as, if we imagine that Z is fixed, then we kind of have just a single component in X, a component of a single image, where the final layer has weights that depend on the second image, the second input. So we can consider this as a component of a single image that where the weights are a function of another image, which is kind of interesting. And so, well, why do we only do this at the last layer? Our idea is maybe we can take an earlier layer and also estimate the weights of an earlier layer from the exemplar. Okay, and so that's how we arrived at this idea of learnets. Okay, so I'm going to show here, we have on the left the Siamese architecture, and on the right the learnet architecture. So the basic idea is, with the Siamese network, we have some parameters W that determine the feature embedding before we compare the two representations. But what we propose to do is, rather than have a fixed W that we use for both branches of the Siamese, we're going to actually make the parameters to the X network depend on the image Z through another convnet. So this is kind of a generalization of the Siamese architecture, where we're going to modify the parameters of an intermediate layer conditioned on the exemplar Z. And so in the diagram, you can see this as the red convolution box. So it's showing that this particular going to cross-correlate or compute a convolution where the weights depend on another input. And so it's still a directed acyclic graph. So there's no reason that you can't do backpropagation on this model. And that's the approach we're going to take. Okay, so that's simple enough. But I guess the questions that remain are, can we do it? And does it work? But first, I was going to address a kind of a philosophical question, which is this learnet thing really learning to learn? Controversial, and maybe there's not too much point arguing about it too much. But one interesting perspective is, what does it mean to learn? How do we define learning? So if we define it as some procedure that takes a set of examples and maps it to a function, then yes, that's basically what it's doing. It's taking like the set of offline examples plus one new example and giving out a function that depends, that maps inputs to a score. So in a way, I mean, in the same way that machine learning is learning, learnets are learning, but it's not the kind of learning we're used to, I guess. Yeah, but it's interesting to think about. Okay, so now on to, can we actually do it? So there is a bit of a practical complication with implementing this, and you might have thought of it already. So like the number of parameters in a convnet is very, very large, okay? So if we consider like a normal fully connected layer, it might be something like 4,000 by 4,000. So it's going to be more than 10 to the 7, which is quite large. For a convolutional layer, it will be a bit less, but like a normal intermediate convolutional layer might be 3 by 3 spatial support, and then mapping 192 channels to 256 channels. So also 10 to the 6, 10 to the 7 parameters. So that's quite large, but then if we think about a convnet that outputs this number of variables, then the layer which outputs that many variables itself has to be very, very big. So if you imagine mapping from a final fully connected layer, so 4,000 dimensions, and we map from that to 10 to the 6, 10 to the 7 outputs, we're going to have a very, very big layer. So this layer is going to have 1 billion parameters in itself. And that's going to be quite not a completely unmanageable amount of memory, but pretty difficult to deal with, pretty annoying to save models and load models, and yeah. So, and it might also be prone to overfitting because of the sheer number of parameters that this would have. So we started looking for ways to make this more tractable, to reduce the number of parameters that we have to predict. And so we arrived at factorization. So what I'll do is I'll go through first the factorization that we consider for a simple fully connected layer, and then I'll talk about extending it to the convolutional case. And actually tricks like this have been around, so this is not completely crazily novel, but it did serve the purpose that we needed. So the idea is if we consider a fully connected layer as W, it's just a matrix multiplication or matrix vector product. So we're going to compute W times X. And of course, any matrix W can be factorized by the SVD into a basis times a diagonal matrix times another basis. And so our idea is we're going to predict constant, or we're going to learn constant bases, M and M prime. So these will be parameters that we learn during the offline phase. And then in the online phase, we're only going to compute the diagonal part of the transform as a function of the other image. So it's a little bit complicated. So I'll just go through it again. So the M and M prime are fixed as a result of training. And then at test time, we'll compute the diagonal, the premise of the diagonal, as a function of the exemplar Z. Okay, so I hope it makes sense. We're also going, and as you can see, like, whereas a matrix that's n by n would have n squared parameters, a diagonal matrix only has. So this solves essentially the problem of the large number of parameters that we have to predict. And of course, we also predict the bias, but since the bias doesn't have this n squared problem, I've just left it out of this formulation for clarity. Okay, so that's how we could make it much easier to predict a fully connected layer. But now if we want to predict a convolutional layer, what should we do? And this is kind of inspired by the residual blocks in ResNet. So our idea is we'll replace that first matrix multiplication with a 1-by-1 conv. And then we're going to do something which we call a diagonal conv with m by m spatial support. And then after that, we'll do a 1-by-1 conv. And only the diagonal conv, which I'll explain in a second, will depend on the exemplar image Z. Okay, so what is this diagonal conv? What I mean here is, whereas a normal convolution in the multi-channel case, every output will depend on all the channels of the input. But with a diagonal conv, we're just going to convolve each channel with one filter. And so this is kind of illustrated below here. So the first convolution is a normal dense convolution where each output depends on every channel of the input. And then we're kind of going to split the channels out and convolve each one with a different filter. Of course, like the filter is different for each channel. And then after that, we're going to reassemble it into an image and compute a normal convolution where each output depends on every input channel. And altogether, this kind of has the same support as a normal conv, but that diagonal conv captures the spatial support, but without having too many channels. So it essentially reduces it by, instead of being quadratic in the number of channels, it's just linear in the number of channels. Okay, and so, yeah, hopefully this kind of makes sense. And I'll just mention a quick implementation detail. That diagonal convolution layer, which involves convolving each channel of the input with a different filter, doesn't really have an efficient primitive in cuDNN. So to implement it, we ended up just essentially constructing a dense convolution and filling it up with zeros in the off diagonals. But this is a little bit inefficient. We didn't have any problems with speeds, so we just used this. But it's conceivable that you could, write your own CUDA kernels and maybe make it a little bit faster, a bit more memory efficient. But since it was basically fast, we just did this. Okay, so I'm about to go to the experimental results. But before I do, I just wanted to introduce a third variant of the architecture. So you can see on the left, the two architectures I've introduced so far, the baseline Siamese network and the learnet, where the yellow network omega sets the parameters of the other network, which we call sometimes the pupil network. So the idea of a conditional embedding or a Siamese learnet is that Siamese network. So you have parameter sharing between the two branches, but then we also have an additional branch which just depends on the exemplar Z, and it sets the same parameters for the two branches of the Siamese network. So this is kind of like a prior that says that you want to apply the same embedding function to X and Z because the function should be symmetric, but we're still going to make a condition on the exemplar Z. And we'll use this in some of the, I'm just introducing it now. And you can see in the formula below, now we have the same function as the Siamese network, except I've replaced the weights W with the same function omega in both cases. Okay, so on to the experiments. So I'm going to present experiments on two different data sets and problems. So the first is the data set Omniglot, which I mentioned at the start, which I'll explain in a second, and object tracking, which is basically the same problem as from Luca's presentation. So now to introduce Omniglot, it's a data set which has many alphabets, so 50 alphabets with a variable number of characters per alphabet, and then 20 examples at least for each character. And so the task at test time with Omniglot is that someone gives you 20 characters from the same alphabet, which is this grid below on the right. And then they give you a query image shown at the top. And you have to identify which of those 20 characters is the match. And there's guaranteed to be exactly one match. So you can see here, if you can find it, the matching characters on the second row on the far left. Okay, and so the chance error for this task is 95% because it's 1 in 20 chance of getting it right. And the network that we're going to use is basically the learnet architecture. So it's 3 convolutional layers to obtain the embedding, and then a weighted L1 distance between the resulting representations. And we're going to use a learnet to modify the filters of conv2. Okay, and I should mention too that the original Omniglot dataset uses images of more than 100 by 100. But here we're just considering like relatively small images and shallow networks so that we could iterate quickly and test different things. So here are the raw numbers. So we have at the top the Siamese network, and then the second row I'm going to explain is it's kind of a baseline which we felt we should compare against, which is a Siamese network with the parameters unshared. So you can have different parameters for each branch. So this kind of has a bit more capacity, but I guess the parameter sharing is also a type of regularization. So it's not clear if this will do better or worse. But in this case, we can see that going from the Siamese network to the Siamese network with unshared parameters, actually, this is on a test set, of course. So we go from about 41.8% to 34.6%, which is quite good already, actually. It's a little bit surprising. And then if we introduce the learnet, where we have a completely different function which sets the parameters of conv2, we get down from 34.6 to 28.6. That's quite a big reduction. And then finally, we tried that, I called it the conditional embedding or the Siamese learnet. We'll use a learnet to set the parameters of both branches. We still have identical embedding functions, but they depend on the image Z. And actually, that didn't help performance here. So yeah, I mean, these are the results. So yeah, in this case, the learnet was significantly better, I'd say. Okay, and so now I'll go on to object tracking. So the problem setup, the training and testing, it's all identical what we presented in Luca's presentation. The network is slightly different. So we have an AlexNet where we actually removed, we went to maybe 50% of the channels in earlier layers and 25% of the channels in later layers, because we just we wanted to try and push for speed at the start. But yeah, So you might notice actually if you compare the results from the Siamese tracking paper and the NIPS paper, actually the Siamese network has better results in the newer paper, just because we changed a few things. So we changed like the network itself, the number of channels. We used a bit more training data, and we also modified how we were resizing the images. So we haven't yet updated the NIPS paper to use the modified code and architecture that we used in the Siamese tracking paper when we were pushing for good results for VAT. So that's the disparity in results. But hopefully we'll get around to updating the results from the NIPS paper too. But the important thing is still that it's an apples to apples comparison in each paper. Okay, and we're going to use learnet to predict conv2. So I've been saying we're predicting conv2. We tried each one, and it seemed that conv2 worked better. But we've only ever tried predicting the parameters of a single intermediate layer. Okay, so on to the results. So you can see the Siamese network. So first I'll explain that we have accuracy, intersection over union, and the number of failures. So these are the two metrics by which trackers were evaluated in VAT. I think it was VAT 15. Or 15? Yeah. 15. Okay, so the Siamese network is achieving, these numbers are not bad actually, like 0.465 and 105 failures. And when we introduce that unshared parameter change, so we're going to use different parameters for each branch. In this case, it actually reduced the performance. So we got worse accuracy and more failures. And we believe it's because the networks that we use for tracking are significantly more complex than the 3-layer network for Omniglot. So probably, while it helped for Omniglot, it's actually useful regularization for tracking to tie the weights in the two Siamese layers. And then we have, so the results, so actually for tracking, the learnet did not do very well. So we don't have the numbers here, but we should get them in the paper. So we just have the results for the Siamese learnet. So that's with the same embedding function that depends on the exemplar image. And if you compare the Siamese to the Siamese learnet, we actually get quite a boost. So up from 0.465 to 0.500, and less failures, so that's great. And now we're just going to show a couple of trackers that were very competitive at the time. So DSST, MEME, muster, DAT, and SODLT. So essentially, SODLT has even better accuracy. This was an online fine-tuning, deep learning-based approach. But besides that, we're actually getting very, very good accuracy with the Siamese learnet. And in fact, it achieves the lowest number of failures out of these trackers. So it is a competitive method, and introducing the learnet is actually giving us the boost to go from quite good to almost the best, not in all metrics, but yeah, so it's good news. And finally, we decided to actually delve into the network to verify that these filters that we're predicting are actually having an effect in the intermediate activations. So what we're going to show here is at the top for Omniglot and the bottom for the VAT data. I'm sorry, the ImageNet video data. So at the top, or in both, we have different exemplars, Z, and then the same candidate X. So we're going to see if the filters that we get are different for different exemplars, and then if the response of the network to the same input changes. And so, yeah, at least we want to see that they're different. If they're not different, then it's not working at all. But it's kind of encouraging to see that changing the exemplar does lead to filters. And then the activations that we get in response to the same image X do change. So yeah, this is good news. Just a sanity check. Okay, so to conclude, we'd basically say that learnets are an intriguing generalization of Siamese networks for problems involving one-shot learning or any kind of relationship between pairs of things. There's still a lot left to explore, like Some obvious things which we mostly haven't